Hello my dear students, welcome back to Fluid Mechanics lecture series. I am your Sumam. My channel name is also Sumam. You can watch my videos on my channel. So if you found useful, please don't forget to like, share, comment and subscribe. Your comments are highly valuable to me. All the related problems are discussing in the incoming videos. The topic for today's discussion is Fluid Kinetics. This is the third part of fluid mechanics. So the first part of fluid mechanics we have discussed already, that is fluid statics, which deals with the fluid under rest. Since the fluid is under rest, there is no relative motion of the fluid particle or there is no shear force. But the fluid under rest has significant surface force which arise solely from the action of normal stress, that is hydrostatic pressure. So we have learned previously that pressure intensity at any point in static mass of fluid depends upon its position with respect to free surface and specific weight of the fluid. So intensity of pressure increases when we move down in static mass of fluid, or it depends upon the depth of submergence. So in fluid statics we have discussed about hydrostatic law, the pressure measuring techniques, the action of fluid pressure on surfaces, that is horizontal surface, vertical surface, inclined surface and curved surface. The method of computation of hydrostatic force and pressure distribution on submerged surface that help the design of structures and equipments like hydraulic devices, storage vessels, dams, that also explained in fluid statics. Fluid kinematics mainly deals with the motion of the fluid without considering the forces which causes the fluid motion. It studies how the fluid flow and how to describe the fluid motion. So that means, kinematics describe the geometry of the fluid particle in motion in terms of displacement, velocity, acceleration without considering the forces which causes the motion. Whereas in fluid kinetics, we considered the forces which causes the fluid motion. The dynamics of fluid motion deals with the fluid kinetics, which relates fluid kinematics with the forces which causes the motion. This relationship of fluid motion is established by the use of laws of nature. They are conservation of mass, that is the continuity relationship, Newton's law of motion, the first and second law of thermodynamics. In addition, we have to consider the boundary condition, that is no slip condition. That is, the real fluid has zero velocity at the boundary. The dynamics of fluid motion is governed by a set of equations known as laws of motion. So these equations are obtained by using Newton's second law of motion, that is F equal to ma. The various forces which are acting on the fluid during its motion are represented by F equal to Fg, that is the gravity force due to the weight of the fluid, and Fp, that is the pressure force, that is due to the pressure gradient that exists in the fluid flow when the fluid is in motion, and Fe, that is the viscous force, that is due to viscosity. So real fluid possesses viscosity, so Fe represents viscous force. Ft, that is the turbulent force. So when the flow is turbulent, the fluid particles are moving in zigzag manner or in random manner. So there is a momentum transfer taking place when the particle moving from one layer of the fluid to other, that is due to the turbulence in flow. So Ft represents the turbulent force and Fs is surface tension force, which is due to the cohesive property of the fluid, and Fe represents the force due to compressibility. When the fluid is compressible, or if the fluid is of elastic nature, we have to account the force due to compressibility. The force can be represented in x, y and z direction. So in that case, it is Fx, Fy and Fz correspondingly. So all these forces has the component in x, y, z direction. So Fx equal to Fgx plus Fpx plus Fpx plus Ftx plus Fsx plus Fex, and so on and so forth. Suppose there is enough depth of flow, the surface tension force is not significant. Similarly, if the fluid is incompressible, the force due to compressibility can be neglected. So in that case, we can apply Newton's law as ma equal to Fg plus Fp plus Fe plus Ft. So this equation is called Reynolds equation. If the turbulence is not significant, then we can eliminate this term. Now this equation becomes ma equal to Fg plus Fp plus Fe, and it is called Navier-Stokes equation. So in this equation we consider the gravity force, pressure force and viscous force. So in the case of ideal fluid, there is no viscosity, so we can eliminate this term. So this equation turns into ma, that is equal to Fg plus Fp, and that is called Euler's equation. In x direction, Euler's equation can be written as m into ax, that is ax is the acceleration component in x direction, equal to Fgx plus Fpx. The next part is the derivation of Euler's equation. So how we can derive the Euler's equation of motion? Euler's equation of motion is established by applying Newton's second law of motion to an element of fluid moving within the stream tube. So consider a fluid element of having mean area dA and length ds. So the pressure force that is acting on upstream and downstream phase is P into dA and P plus dP into dA. So weight of the element that is acting down. So dA is the mean area and ds is the length of this element. Then weight of the element, that is W, that is equal to rho g into, rho g indicates specific weight into volume of this element, that is dA into ds. Another force, that is friction force, that is opposing the motion of the fluid. The centroid of the downstream phase of element is at a level dz higher than the centroid of the upstream phase of the element. So theta, that is the angle which makes the axis of the element with respect to horizontal. So if you are completing this triangle, this angle is also theta. So if you are considering this triangle, then sin theta, that is equal to dz by ds, or ds sin theta, that is equal to dz. Similarly, if you are considering this triangle, then the component of the weight that is acting along the axis of the element, that is equal to W sin theta. Now we can consider the forces acting on this element to apply this Newton's law of motion. So net pressure force that is acting on this element, that is equal to P into dA minus P plus dP into dA. So that is equal to minus dP into dA. Capital P represents the perimeter of this element. So P into ds represents the surface area. So shear force dFs, that is equal to shear stress into surface area. So that is equal to tau into dP into ds. The component of the body force along this axis, that is equal to W sin theta, that is equal to rho g into dA into ds into sin theta. So if you are applying Newton's second law of motion, then adding all these forces, that is net pressure force and tangential force and body force, that is equal to minus dP into dA minus tau into dP ds minus rho g into dA into ds sin theta, that is equal to rho into dA into ds into as. So this term, that is rho into dA ds, represents mass and as represents the acceleration component in any spatial direction. Relative motion of the fluid particle thus not fixed and it varies from time to time. So if you are considering the velocity of the fluid particle, it is a function of space and time. So change of velocity equal to total change of velocity with respect to space and time. So in that case, acceleration is a summation of convective and local acceleration. Since the flow is steady, this term, that is local acceleration, that is equal to 0. So as equal to u into dou u by dou s, or as is equal to convective acceleration. So since it's a function of space only, then this partial derivative can be replaced by total derivative, that is as equal to u into du by ds. So if you are substituting as u into du by ds and replacing ds sin theta by means of dz, this equation now turns to minus dp dA minus tau into dp ds minus rho g into dA dz equal to mass into acceleration. So summation of pressure force, viscous force and gravity force, that is equal to mass into acceleration. So if you are dividing this equation by means of rho into dA into ds. So rho into dA ds represents mass of this fluid element. Then this equation now turns to u into du by ds plus 1 by rho into dp by ds plus g into dz by ds equal to minus tau by rho into dp by dA. For ideal fluid, viscosity equals 0. So for ideal fluid, this term that is equal to 0. So this equation becomes u into du by dx plus 1 by rho into dp by ds plus g into dz by ds, that is equal to 0. Or we can rewrite this expression as half into differential of u square plus dp by rho plus g into dz equal to 0. So this is a derivation of Euler's equation by applying Newton's second law of motion to an element of fluid moving within the stream tube. So this equation, that is Euler's equation, is integrated along a streamline. We can derive the Bernoulli's theorem by integrating this expression. Integral of half into differential of u square plus integral of dp by rho plus g into integral of dz, that is equal to constant. Or we can write this expression as u square by 2g plus p by rho g plus z equal to constant. So in more general form, we can express this equation as v square by 2g plus p by rho g plus z equal to constant. So v square by 2g, which indicates the velocity head, that is the kinetic energy per unit weight. Similarly, p by rho g, which represents pressure energy per unit weight, or it is called pressure head, and z, which indicates the position head or elevation head or geodetic head, that is represents the potential energy per unit weight. So summation of kinetic energy per unit weight and pressure energy per unit weight plus potential energy per unit weight, that is equal to constant, or total energy at any point is constant. So Bernoulli's equation states that for a steady irrotational flow of incompressible fluid, total energy at any point is constant, or the summation of kinetic energy plus pressure energy plus potential energy is a constant. So this equation is derived based on certain assumptions, or this equation is valid under these conditions. They are: flow is steady. So that is, flow and fluid properties are constant with respect to time. Next is flow is ideal. That means there is no viscosity. That means there is no shear force or there is no frictional force. Now flow is incompressible. That means density is constant. Flow is one-dimensional. So that means this equation is varied along a streamline. So for a streamline, this total energy is a constant. Flow is continuous and flow is uniform over a section. Then only gravity and pressure forces are present, because Bernoulli's equation is obtained by integrating Euler's equation along a streamline. Euler's equation considers only gravity force and pressure force. So these are the assumptions, and this equation is valid under these assumptions. The summation of pressure head and velocity head and position head, that is called total energy head, is represented by H. So here P by rho g plus Z, that is called piezometry head. So if you are applying this Bernoulli's equation at 2 points in a flowing fluid, as shown in this figure, that is 1 and 2 are the 2 points, then we can write P1 by rho g plus V1 square by 2g plus Z1, that is equal to P2 by rho g plus V2 square by 2g plus Z2. So if the pipe is horizontal, then Z1 equal to Z2. So our equation becomes P1 by rho g plus V1 square by 2g equal to P2 by rho g plus V2 square by 2g. So if any change occurs at the section 1 in the cross section, the corresponding change that will come to this pressure head to balance this equation. So that means pressure and velocity are directly connected. So this concept along with the content equation we can use as a principle for the flow measurement techniques that we are discussing in the subsequent videos. So real fluid possesses viscosity. So if you are considering real fluid, then the loss is taking place when we are moving from section 1 to section 2. So this Bernoulli's equation is now modified for real fluid as P1 by rho g plus V1 square by 2g plus Z1 equal to P2 by rho g plus V2 square by 2g plus Z2 plus HL. So HL, that is the head loss for the fluid when it flows from section 1 to section 2. Bernoulli's equation can also apply for a compressor fluid. The flow of compressor fluid may take place with isothermal or adiabatic changes of volume. So when the volume changes, correspondingly there is a change in density. So the Bernoulli's equation is now modified as the first term, that is pressure head, is modified as integral of dP by rho plus V square by 2 plus Gz equal to constant. So the integral of dP by rho considers the corresponding changes in density with respect to change in volume. Now the session comes to an end. My next video regarding energy correction factor. All the related problems are discussing in the incoming videos. For the time being, it is enough. Thank you.